So what we've been doing is progressively relaxing all our assumptions. So towards that, let's just draw this picture. And let's think about all the assumptions that we've been making. Now, we started out with, for example, a CSTR, right? Let's talk about this in the context of the CSTR. And we had an assumption first that the temperature was fixed and constant. So that was the first assumption, T fixed and constant. And we assumed that we were not adding or removing energy from this reactor. So that was the first, that's what we started out with. Then we said, well, T is not fixed, and there's a whole plane of isorate lines to consider, plane of isorate lines. So that was the second thing. And even in the case where we were not adding heat to the reactor itself, we had interstage coolers, but we didn't add heat to the reactor itself. So then we could develop the expression. What we showed just now was T is changing due to the addition of heat. So when we were adding heat, then we could still determine the temperature change with time. And of course, associated with that was that the conversion was also influenced. So that was another function that was affected by the heat added. Now, the big assumption behind all this was that we had ideal reactor types. And of course, the ideal reactors that we had were CSTR, EFR, and batch. So those are the four we've been talking about. But of course, the real world is not any one of these, right? If you were to construct a real reactor, so if you tried to produce, for example, a CSTR, then you start with some container, you stick a stirrer in, and you have feed flow in and out here. And so let's say your liquid level is here. And so you are performing mixing in this reactor. But of course, you cannot do infinite mixing. You cannot get ideal perfect mixing in this reactor because it would take an infinite amount of energy to completely mix this reactor so that at any point in time, you can say at every point in that reactor, you have the exact same concentration. In the real world, as your components, as your feed stream enters, it is going to give us a higher concentration near the feed point. So we will have some zone here, and we don't know how big this zone is. There will be a zone here where you have a relatively high concentration of reactant. And so there is going to be, in the real world, a change of concentration. There's going to be a concentration gradient across this reactor. There are other things that could complicate it. So the real world reactors have internals, and there are other functional elements there which will interrupt the flow. And so you may have low flow regions in that reactor where things, for example, are circulating around. You can imagine some corner here where things are staying for, the fluid is remaining there for a relatively long period of time. And you could think of this then as a kind of little batch reactor that's sitting down here. There may be the possibility of short circuiting, which means that your fluid comes in here, but because your entry and exit points are close together, perhaps, that it's possible for some of your fluid to skim past the body of the reactor and appear at the exit pretty quickly. In this case, it's almost like plug flow. So in a real reactor, we likely have some combination among the three ideal reactor types that we presented. So that's the complication that we have now, that nothing is a perfect CSTR, nor is anything a perfect PFR. Remember, the PFR stayed perfectly segregated all the time. And if you think about a fluid flowing in a pipeline, right, which is perhaps the closest thing to a PFR, imagine a long pipeline, then even in the most benign situation, right, where you have, for example, laminar flow, right, even in a nice gentle laminar flow situation, you don't have plug flow. In a laminar flow situation, you have regions where the velocity is high and regions where the velocity is low. You've got a parabolic profile there. And so it's very rare to get this kind of perfect plug behavior. Nothing ever stays in a perfect plug like this. And even if you didn't have laminar flow, even if you had turbulent flow, which is a bit more like the velocity profile, even though it's turbulent, in some ways you can think of it as having the same axial velocity. Even in that case, you still have molecular diffusion. So you have diffusion that's superimposed on top of your bulk movement of fluid. So nothing is a perfect PFR, nothing is a perfect CSTR. Of course, in the batch, we can anticipate that the batch reactor, that is going to, you can stop flow in and flow out, but then the same mixing issues arise, okay? So we have the situation where nothing in the real world is ideal, and we have to recognize that we have some weird combination of things going on. In other words, we have imperfect mixing. So what I'm trying to show here is that we have been progressively relaxing our key assumptions until we arrive at a model of a reactor, which is more and more like a real world reactor. And so in the case that we are talking about now, we are dealing with the assumption of ideal flow. So now we are introducing this topic of imperfect mixing. And a powerful tool towards imperfect mixing is the notion of residence time. And we have, of course, introduced residence time before. We had introduced tau. So we said tau is the space time and tau is the volume over the volumetric flow rate. So this was a nice, easy one. But this, in a sense, gives us a very overall or a very summaric view of the age in the reactor. It's just giving us the average age in these reactors. So what we want to do now is understand all the ages that occur in each of these reactors or in real reactors. In other words, if we think about an age distribution, right, let's let theta be the age. If we think about an age distribution, then we have to acknowledge that in any reactor, a certain age distribution applies. And I'm just going to write this as a fraction here. So in the reactors, a certain age distribution applies. And age distributions apply in any space, even in this Zoom session. If you look at the distribution of ages, let's say all the people in the room, that's the age, and this is maybe the number of people. Then you've got until, right, nobody here, I think, is of age 0. Nobody here is of age 10 years old. And then maybe we get a big spike of people of around 20, what would you be? Yeah, around 19, 20, 21. So you'll get a big spike of people in that age range. And then if you carry on here and we don't know how far, but there'll be a little spike. There'll be one person here of a slightly greater age. And so you have an age distribution that looks like this, right? If you look in your home, there'll be another age distribution. So in the reactor of your home, you'll maybe have a couple of people around age 20 and a couple of people of another age. And then maybe there's a third generation at home as well. So you could have an age distribution like that. So we have all these possible age distributions, and these affect the performance of our reactor. So by the end of the day, in this reactor, we want to know what's the reaction rate, right? This the reactor says, or your engineer boss says, that's all very interesting, but what's the total rate of production of this reactor? So the production rate is influenced by all this. For the packets of fluid that have spent a greater period of time in this reactor, there is a greater conversion in those. For the packets of fluid that zoom straight to the exit, they haven't spent much time converting, so they will be converted to a different extent. So resulting from the age distribution, we achieve a certain overall conversion. So I'm going to emphasize that this is the overall conversion with this overbar. So the overall conversion X is influenced by the individual conversions from each of the fluid elements there. Right, so age distribution, and perhaps we can't see the link completely as yet, but we will find that age distribution is a useful way to deal with imperfect mixing. Okay, any questions or comments on any of that so far? Okay, now the next step then is to define for ourselves some useful ways of developing an age distribution. And of course, there is this set of notes here, but in a way, I like to do this from scratch. So we have defined one variable already. So theta is the age of something. So we can say age. So age theta is the time spent by a something. And so instead of saying a something, we'll say an entity is the time spent by an entity in a space. Now, in a space, that's important, right? We have to specify where we are talking about when we say it's the time spent by something. So, for example, we have an age that we can define. So let's take this classroom example. We were talking here about the number of people of certain ages. Now that age that we are defining there is the age of ourselves and how long we've been born here, right? Here's where it gets a little bit metaphysical, but we are here in Africa, and so we came from somewhere. So I don't know if I need to go this far, but we came from somewhere, so we are born here, and so we've been living. So if you were to plot with time our age, we were born at a certain time, and then we started aging in that space. And how fast do you think we were aging? Right, sounds like a silly question, but how fast could you say we were aging? Any takers? Going once, going twice. So we are all aging at the rate of 1 second per second, right? Every second that goes by, we get older by 1 second. Of course, in physics and, well, it's not about physics, but if you are moving close to the speed of light, then to and to another frame of reference. Then you have to specify what frame of reference you are observing from, and then it's more complicated. But leaving that aside, if we just think about normal operation, yeah, we are just aging at the rate of 1 second per second. Okay, so some of us entered at a time around here. So most people in the room have entered at a time maybe around here. And then, so there's a certain distribution of people that entered the world reactor at some time there, and some may have entered much earlier than that, and some, so anyway, you've got different times of entry to the space as well. So you could say the age is related to the real time in this way. So your age, theta, is equal to the current time minus your birth date, right? Your T0 in the world, your birth date. If you take the current date and subtract it from your birth date, then that will give you your age. And so by age, we mean by default, the time we've been living here, right? But there are other ages that we could also define. So instead of defining it like this, we could also ask, what's our age in this room? So in this Zoom room, we have been here for different periods of time. So some people came quite early, maybe about 5 people were here between time close to 0 and then to that time. Then a large number joined around this time, and then a certain other number joined a bit later. So overall, this is the age distribution in the room. And it's actually the reverse of what I've been saying here. So the ones who joined later, so this is actually more like joining time that I'm drawing here. So the number who joined at a certain time. So in terms of age, the number of people who joined later, they are in a sense younger in this room. And you could say maybe they are fresher. They haven't been listening to me droning for so long. So there are, so there's this number of people who are younger in the room. Then there is a certain number of people who are here of kind of middling age. And then there's a certain number of people who have been here for longer than others. So this is pointing out that your age, in terms of how long you've been alive, can be different to your age in a certain space. So the age distribution does depend on your choice of space as well, right? So when we talk about an age distribution, it does matter where we are looking at it. And so, for example, you can define an age distribution inside of a reactor, and you can define a different age distribution at the exit of a reactor. And we'll show that in some cases, those are not the same thing, right? So you get different age distributions, even when you are talking about the same objects or the same entities. So that's another concept, that you have multiple age distributions that are possible. And we are going to define I of theta to be the age distribution inside the reactor. And by the same token, we can define the age distribution at the exit of the reactor. So this is not inside the reactor, right? So we define the age distribution at the exit of the reactor to be E of theta. And these are real distribution functions in the strict statistical sense of the word. So NH, or let's just say a distribution f of x is defined such that f of x And strictly speaking, we should say integrated between, is defined such that if you define it between x and, let's say it that way, so between, so if you are integrating between x and x plus delta x, let's just be extra careful. So it's defined such that if we integrate in this way, we obtain the fraction of entities in property range x and x plus delta x. Okay, so what we are saying here is that we have some distribution function. Let's clear some room here. So we are talking a bit more abstractly now, and we are talking about some arbitrary distribution function f, and it's some variable x. So for example, it could be distribution of heights. So we don't really have people of 0 height. They probably start around maybe 1.4, and then you get a certain, it's not so vertical. And then you get some distribution like this, right? So if x, for example, is height, then your distribution function f is not the fraction by itself. So you can't, for example, say, okay, I want to know exactly how many people are of height 1.5 meters or something, right? You can't look at this and say, okay, at 1.5 meters, I have exactly 0.4 people, right? You can't define a fraction based on an exact value like that. Because if you think about, for example, your age example, if we were to ask how many people are of age 20, what's the fraction of people of age 20 in this are of age 20, let's just say, then we are not able to answer that if we mean exactly 20. So if I asked you right now, how many people are exactly 20 years old? It means it's not even a 1 second gap in there. How many people are exactly 20 since they've, whenever we say age 20, we mean over a 1 year period, right? We mean that you were born less than 12 months difference from where 20 is. So whenever we talk about a fraction at a certain value, we always talk about a range of values. So if we are talking about a specific, so we can't talk about a specific age. So if I were to ask you how many people are of age exactly 20, by the time you answer me, some time will have passed and your answer won't be valid anymore, right? And even if you try to anticipate how long it will take, less than a fraction of a second later, the answer wouldn't be valid anymore. So in any distribution, we are not asking for the fraction at a very specific value. We are always asking over a certain range. So that's why these functions are always defined implicitly, in other words, over a certain range of values. So we can answer, what's the fraction of people? When we say 6 feet, we mean between 6 feet minus a certain number of inches and 6 feet plus a certain number of inches. So that is the resolution. We have to define the resolution over which we are asking the question. And of course, you might be saying, well, aren't you just over defining everything now? Do you really need to think about things at this level? And we do need to for this section, because we need to be very precise about this if we are going to create a distribution function that's useful for our purposes, right? So we define our functions, our age distribution functions, such that, so we say such that I of theta times delta theta is the fraction of, and we'll just call them fluid elements. So those could be packets of fluid, or they could be particles or oil droplets or whatever. So we're just generalizing and saying fluid elements. So it's the fraction of fluid elements that have been in the reactor between ages theta and theta plus delta theta, right? So it's an implicit definition, right? We can just call it an age distribution, but in terms of getting values out of it, we actually have to always operate on it to get something like the fraction of things that are in the reactor. It's always over a certain age range, right? So that was a little excursion into distributions. And by the same token, we can define E of theta. So we define E of theta such that E of theta delta theta is a fraction of fluid elements that appeared at the exit of the reactor. And we should say here, having spent time of theta to theta plus delta theta. And we could also say having spent time is, that's where the term residence time comes from. So residence time, how long have you resided in a space? So what was your residence time in that reactor? So this is the so-called external residence time distribution, external RTD. And this one is the internal RTD. Okay, so those are the two things that we are looking at. We want to know what's the internal RTD and what's the external RTD for our reactors. Let's see. There was this nice practical that used to be done. I'm not sure in these days of remote operation. Have you been doing this? Maybe thumbs up. That practical on RTD. Has anyone done that practical on RTD?
Yes.
Okay, so that practical is running. So that's good. That's a good, it gives you a good impression about many of the things we'll talk about. So remember, in that practical, you were injecting salt dyes and you were measuring conductivities. And so that gave you a sense of how long that salt spent in the reactor. So when we talk about injecting salt into a reactor, we are trying to solve a specific problem. So we've got some real reactor, and we don't know how things are mixing in this reactor. And we are feeding in our fluid, and we are removing fluid here as well. And we would like to know what the age distribution looks like in between. So let's just say the internal one, that's what we are hoping for. So we would like to know what this distribution is. So we're just drawing something up for now. And if you think about this, you are feeding water. Let's say it was simply water being fed through this system. So you are feeding pure water in, you've got pure water in the reactor, and pure water is exiting. If you look at this reactor, there's no way to distinguish between molecules of pure water there. You can't look at a molecule and say, oh, this one has been here, it's very old in this reactor, that's an old water molecule, or there's a young fresh water molecule, right? And I know we talk about fresh water, but typically that's, nothing weird is growing in the glass because we've left it out too long. So that's not the situation here. Here we've got pure water passing through the system. There's no way to label any of that water, or there's no way that we can start to think about getting a curve like this until, of course, we tag some of that water. So normally we have all these elements, if we can call them that. We've got little packets of water entering this reactor. So we've got all these little packets flowing in to the reactor. And then what we do at some instant in time is we inject a little salt into the feed stream. So we inject salt over a very short space of time, over a very short period of time. And we have then, in effect, tagged one of these elements with salt, right? And now we can say, well, there is something chemically different that we can see. And so this packet of salt that has just entered the reactor is going to distribute itself in some way. So in some parts of the reactor, that salt will spend a bit more time. In some parts, it will spend less time. And by the end of the day, all I need to do is sit out here and record the amount of salt that's passing through this reactor. And if I measure the concentration like this, so I measure it as a time profile, then I can start to think about what the age distribution looks like in that reactor. Because if that salt is well mixed with the water, right? It's not like I throw a bunch of rocks in, right? If I threw rocks in, then that will totally mess up the way the water is flowing through this. So I didn't do that. I pulsed a little bit of salt in, it mixed well, and it just joined the stream. And so that in what's flowing through this reactor, we have a certain flow structure that applies in this reactor. As we said before, we have regions where things are flowing through pretty quickly. So some parts of that fluid are flowing straight to the exit. Some parts are circulating around a bit. Some parts are stuck in the corners. Some parts are like plug flows. So you've got all that going on. So now that we've tagged one of those, that is also going to split up and it's going to join. So some parts will be circulating here. Some parts of the salt will be circulating there. Some parts will be chugging straight through. And so in other words, this salt is nice and representative of the water. If it has mixed well with the water, it's quite representative of how the water spends its time in that reactor. And the advantage of the salt is that we know when that salt entered that reactor. So we can say we have managed to tag just one group of fluid elements. So that salt is representative then of every packet of fluid elements. So if you take any other packet, you could say, well, there's no difference. I could have tagged this packet of fluid elements or this packet of fluid elements. In other words, by looking at the profile I get from just one trace of salt at steady state, I can then understand how every packet of water comes in and spends time. In other words, I have deduced the age distribution for the entire reactor, for all the water that passes through here. And it's still a bit of a leap to say, I know about the age distribution. I know about a concentration profile so far. So let's see how we can translate a concentration profile into an age distribution, right? What we actually want is I and E. What we know we can measure in the real world is concentration and time, right? So let's see how those are related. Towards that, let's see, maybe we can. So here's a nice picture from computational fluid dynamics. It's showing you the flow, circulation patterns, and so on. So this is the type of thing that applies in the real world, right? So we've said all this stuff. Yeah. So here, so you can read, these are all other ways. So in previous years, I had other ways of explaining this. It's not like I kept track of which is the best way. So these are also reasonable ways to explain all this stuff. So let's think about our salt tracer now. So let's define for ourselves. Well, we've already defined E of theta such that E of theta delta theta is the fraction of fluid elements that have spent between theta and theta plus delta theta time units in the reactor, right? Now, what we have here is a concentration with time profile. So that's our salt concentration profile. And what we can do is identify on this profile the time at which we pulse the salt into the reactor. So there's a certain time when we did this injection. So we injected into the reactor here at a specific instant in time t0. It took some time for the salt to pass through, and then we started to see salt at the exit. Now we could say that I can estimate the number of moles of salt that spent between a certain age in the reactor. So let's say I take this zone here, and I say simply that the age of the salt that exits in this range, that age is nothing but T minus T0. So if I were to take the time here and subtract it from T0, that's an estimate of the time spent by the salt here. And of course, we are really talking about a time range here. There's a small series of values. So T here is a range of values. So we can say, here, so let's just call this here, pulse tracer interpretation. So our so we pulse in at T0. We are now looking at time T at the reactor. The salt will have spent T minus T0 time units in the reactor. Okay, so that's the age. So we can say beta equals T minus T0. That's fine. But what we really want to do now is estimate how much of that salt. So we can say the moles of salt of age beta. And here we need to specify a range. So it's a range of theta and we're just going to call it theta to beta plus delta beta. So there's a certain number of moles of salt that have spent between those ages there. And that's going to equal the concentration of the salts that we've measured at time t. So it's really the average. So I'm going to say bar here. There's an average salt concentration between T and T plus delta T, right? So by this, I mean there's a time range, and so there's an average salt concentration. And if we want to convert a concentration to moles, we need to multiply that by a flow rate, right? So this flow rate, that's going to give us cubic meters per second. So this is still moles per second. What we actually want is the number of moles in that age range, delta theta. So if I multiply that by the time range, delta theta, then this product is the volume of fluid that has exited during the time span of interest, delta theta. So that volume times that average concentration that we measure over that, and we should make this a delta theta as well. Sorry, delta theta. So over that time span of interest, there's a certain concentration, an average concentration that we can see. So that concentration times that volume, that's the number of moles in that range. So then the fraction, we can say the fraction of fluid at that exit. And we know that the fraction is actually E of beta times delta beta. So that's the fraction that's appearing at that exit. That's going to equal this number of moles divided by the sum over all possible contributions. So if we add up all the moles that we see over all ages, right, if we take the number of moles in a specific age range and divide it by the sum over all the moles, then that is going to be the fraction of fluid that exited between theta and theta plus delta theta. The denominator here, I should really write in a better way. So we should call this the integral. So that's the integral of the number of moles in theta d theta. Right, so that's what we are looking for. And then if we write this in terms of measurable things, this is what we have here. So that's the number of moles there. Oops. Sure. This is one of the painful parts of remote teaching, is working with this editor. Okay, so that's there. And here, yeah, well, we're going to improve that just now. And of course, the variable here is t. We don't like working in t. We would rather work in terms of theta. We don't want to write this as theta plus t naught. That would be tedious. So let t naught equal naught. So we can simply define our time to start from 0. Or in other words, these t's, if we just subtract t naught from it, then we can get rid of that t naught. So let t naught be theta, t naught equals 0. So then that will give us that t equals theta. Okay, so we can write this as theta. Should have really used it. Copy paste thing from earlier. So that's there. There are a couple of, well, by the way, this delta theta is wrong. We are integrating in theta, so this integral is the sum there. So that's fine. This q is a constant, so we can cancel numerator and denominator, and then this average here. So instead of saying the average, we'll just call this the concentration of salt at age theta. And this the same story. So if you look at this, it's telling us that we can obtain E of theta delta theta simply by taking the curve that we measure and dividing it by the area under that curve. And by the way, we can, let's just get rid of the intermediate step and divide both sides by delta theta. So we don't need the in-between step. And we can divide the delta thetas out here. So if you look at this equation, it's saying all you need to do to get E of theta is take your original curve and divide by the area under that curve. So it's incredibly easy, right? This E of theta thing, which we defined nicely, we had some nice statistical definitions, but we had no clue how we were possibly going to get such a function. And it turns out it's very easy and very practical to do it, right? You've already done it in the prac. You've measured concentration as a function of time. And so it's telling us then, all you need to do is take your original profile, like let's take this one that's drawn here. So you just take this profile that you've measured, then your time values, just take your injection time and subtract it from all these time values so that this becomes theta, so that it's 0 and this whole axis becomes theta. So just subtract T naught from all the values on the x-axis. Then you've got a nice theta curve here. So now you've got C of theta. And then all you need to do is take C of theta and divide it by the area under the curve. And you just take the curve, estimate the area underneath, and that's some number. And so you will get then E of theta. So E of theta is quite easily and practically measured like this. Yeah, and I must say, when I first saw this, yeah, it seemed quite illegal to me. It seemed crazy that you could fully describe the age distribution in any reactor just by pulsing in a little bit of salt or whatever tracer and doing this very simple operation. Do you believe that? Any questions or comments on that? Okay, so if I take that as a yes, then you would say, well, that's half the picture. E of theta, that's one thing, but it seems I of theta might be even more useful, because then we can understand the age distribution inside of the reactor. So towards that, we would like to develop a relationship between E of theta and I of theta. So to do that, first we introduce an idea here. So first we can recognize that if we were to integrate between 0 and, I'm just going to say it that way first. And here. Okay, so think about this integral now. What's the answer here? Right? Any takers for this? What does this thing mean? So remember, E of theta d theta, that's a fraction. Okay, so this is a fraction in a certain age range. And we are looking at all possible age ranges, right? Age starts from 0. We don't really define things of negative age. And then in principle, everything can age off to infinity. We are not putting any upper limit on the age. So we are adding up. That's the way to read integrals, right? We are adding up over all possible ages. So we are adding up all the fractions over all possible age ranges. So what's the sum of all possible fractions equal to?
I think it's the exact age distribution in the reactor. in the exit.
So you are saying it's equal to I. So, I mean, we are looking for this kind of relationship. We are looking for the relationship between E and I. But at the moment, we are just thinking about if we add up over all fractions. So think about, you've taken all the people in the class and you've worked out the fractions in all the possible height ranges, and you add up all the fractions. What happens when you add up all the fractions? Right? The sum over all possible fractions is a 1, right? It's we are simply saying we are adding up all fractions over all possible age ranges. It must add up to 1. So if we add up everything to 1, then if we add up all ages, we get the total amount. And then if we add up to a limited number, so let's say we add up only up to theta, right? And you can do this, so we normally just don't worry about it. Then you can define the fraction that has been in the reactor up to a certain age. So we can think of this F as the fraction that has appeared at the exit up to and including age theta. So that's one interesting fraction. So we can then consider that if we are looking at the exit from the reactor, so some real reactor, we don't know what the mixing pattern is here. So we are feeding and we are observing at the exit. We are going to pulse in a bit of tracer here. And again, we get our trace here. And then we are saying that at the exit, a certain amount has appeared by a certain age. So if we pick a specific age, then a certain fraction has already appeared, right? So that has already appeared by the exit. And so there's a certain amount that's still left over in the reactor. So inside of the reactor, the amount of material that has spent this age can be defined. So we can say that the volume in the reactor multiplied by the fraction that has been in there, by the fraction that is in the reactor between theta and theta plus delta theta, which we know is delta theta, like that. So that's the amount of volume that is left over in that reactor, in that range. Let's think. So that's the fraction that's in the reactor. So that is what's left over in the reactor in that range. And that must equal the total amount that we had originally in the reactor. So that's V, and minus the amount that has left over time. So Q times F theta. So this is the amount, this is the volume that has left. And if we, let's see, we need to multiply by the time range, delta theta. So this balance shows us what's left over in the reactor if we consider what was originally in the reactor and what was removed from the reactor. So it's a simple balance like that. I'm just going to look here. This. Yeah, so that's what we are saying here. We are saying that in the reactor, in that age range, that is the volume of fluid elements there. The total amount that could have entered that age range is this. So Q times delta theta that's the total amount that enters in the first place. The amount that has exited between theta and theta plus delta theta is this, right? So the amount that's left over then is that quantity. So if we group out the Q, then we can say that Q delta theta equals, well, let's do it here. So, and I'm using a V instead of an H, so that's volume. I'm doing it as if it's a volume. And here I should have said Q, right? So Q times 1 minus F theta, and then times delta theta. That is the, so this is what's left over, 1 minus F theta that has not appeared at the exit. Remember F theta, that's everything that has managed to exit. This is what has not managed to exit. Q times delta theta, maybe it's best to write here. Q times delta theta is the total amount that entered in the first place. So this is the total amount that's left over in the reactor, which we know is equal to this. Then what we can do is divide both sides by delta theta. And we can also divide by, let's see which way around, we can divide by Q. So if we divide V by Q, we know we get tau, the space-time. And this F theta, we can replace by this thing. And now we have what we were looking for. This gives us the relationship between I and E of theta.
Sorry to interrupt you eating, but I just came in to tell you something.
Sorry, 1 second. Sorry about that. So here you've got your 1 over tau. So I of theta has this relationship with E of theta. And this is general, right? When we derived all of this, we never said that it's a CSTR or anything like that. This applies to all sum of fractions. This is simply the integral. We can define the fraction that has appeared by the exit. And so there's nothing, and this balance is simply, this is what's left over using all the definitions we've introduced. This is what's left over. This is what must have been left over if we subtract what came in from what left. So this is a simple mass balance. And so this equation has been derived without using any assumption about the nature of the mixing. In other words, this is always true. This is always something we can rely on. And by the same token, this relationship is also always true. We didn't assume anything about this reactor type. And if you think about in that practical, this is what you use to estimate E of theta. You never said, okay, this is more like a CSTR, therefore I have to use this equation, or this is more like a PFR, so I have to use that equation. So this applies to any type of mixing. You can always do this to estimate E of theta, and then you can always use this to estimate I of theta. Okay, and I know we've run out of time there, so we are going to use these relationships in the next session to look at our ideal reactors. So I know we were doing all this to get away from the ideal reactors, but just out of curiosity, let's see what these look like for the ideal reactors as well. Okay, so we'll look at that in the next session. Any questions or comments there?
Oh, sorry, sir.
Yeah.
May I ask if we can look at the H distribution as a probability function?
That's exactly right. So that's why I said, you know, when we introduced this idea about fractions, we introduced this general function. So this is a probability density function. And so E and I are probability density functions. That's right.
So we can be able to to determine dispersions inside the reactor using maybe the variance.
Yeah, that's quite true. So you can, all the statistical operations that you are familiar with, like if you want the mean value, for example, then you can say theta bar equals, and you can integrate this over all possible values. So if you do theta and you would use a theta here and d theta, then this would give you the mean theta. So that's just one example of one of the common operations that you do on probability functions. So you can work out the mean, you can work out the standard deviation. There are lots of operations you can do on probability functions. By the way, can you tell me what this theta over bar should be? So you were asking, sorry, say that again, please.
I think it's the average residence time.
Yes, so that's the average residence time. Yes, that's true. But is this also equal to something else? When we say average, what's another name for average?
Mean.
Right, mean. And what did we say from the beginning was like a mean time or a mean age? So the space-time, right? And the space-time is defined very practically and easily, volume divided by volumetric flow rate. And if you think about it, this is the average time spent in the reactor. So if you look all the way back to the beginning, that's what we said about tau. And now we seem to have a way to estimate that mean. We have a kind of very rigorous way through this density function and so on. And so we are anticipating this. So we are going to, so think about that, see if you can prove it. Think about how would you go about proving this is true, right? On the one hand, this is very statistical, and on the other hand, this is very kind of physical, but there seems to be this relationship. So think about whether you would be able to prove this as well. Okay. So that's one of the things we'll be looking at next. Okay, any other questions or comments there? All right, if not, thank you all for coming and see you next time. My little